Hey everybody. Well, I don't know where it's like where you are, but what it's like where you are, but it's super stormy over here. And as a bad novelist might say, it was a dark and stormy night when we watched a video on probability mass functions. So anyway, with that, let's get started. Okay, so today I'm going to be chatting a little bit about multiple random variables, and basically this is a tool that we use when an event of interest is described by two or more random variables. And of course, random variables are always associated with some probabilities, so we track the probability associated with those two or more random variables by defining either a joint, it's what it's called, joint continuous probability density function, or PDF, or joint discrete probability mass function, depending on whether our random variables are continuous in the PDF case or discrete in the PMF case. And of course, those measures of probability or ways of tracking probability are denoted as follows, kind of in the usual way. So for the joint continuous probability density function, in this case, we're looking at only two random variables. So the joint probability function depends only on random variables x and y. That probability density associated with those two random variables is going to be denoted here by little f, which is going to be evaluated then at a specific value of x little x and a specific value of the random variable y little y. If we have a problem which involves discrete random variables, then we would be looking at a joint probability mass function, or joint PMF. And in that case, we're looking at the probability associated with the random variable x and y taking on a specific set of values xi and yj. We're going to focus in on the probability mass functions because we talked about the joint CDF or PDFs in class, probability density functions in class. And so then for this probability mass function here, really what we're saying is it represents the probability that our random variable x is going to be equal to xi and our random variable y is going to be equal to yj. If we were to represent that graphically, it might look something like this, where we're plotting the probability associated with any given value of xi and yj on this vertical axis against the specific choices allowed for y and specific choices or discrete values allowed for x. And in this case, x and y are apparently representing, the wind is really blowing harder, are apparently representing productivity of some manufacturing process representing percent. And so the discrete values of y that y can take on are 50, 70, and 90%. And then that is related to maybe the amount of time it takes to manufacture a product, or the duration, which can take on this x-axis discrete values of 6, 8, 10, and 12. So for every combination of duration and productivity, we're going to have a corresponding probability, and that's denoted here by the probability mass function P of the random variables x and y. Note that we see there's more probability in certain for certain choices of xi and yj, while there's less probability associated with other choices of x, I, and yj. So now that we've defined a probability mass function, there are a few other things that we can define that are useful. One is this concept of a marginal probability mass function. So in this case, we're talking about a marginal probability mass function of the random variable x. So it's just going to be the PMF of the random variable x evaluated at xi. And it is calculated from the joint PMF by summing that joint PMF over all yj. So if we go back to our figure here, the marginal PMF for x would be basically giving us the probability, say if x was equal to 12, it would be the probability that you're going to get a duration of 12 hours for any productivity. So it doesn't matter, we don't really care what the productivity is, we're just interested in that marginal distribution along X. So we want to know what is the probability associated with the duration of 12 hours. And to get that, we just sum up all of the productivity probabilities along that xi equal to 12 line right there. So that would be our marginal probability of X evaluated at xi equal to 12 hours. Okay, so that's our marginal probability definition. Likewise, we could ask for a marginal PMF of the random variable y, which is going to be denoted here as the PMF for the random variable y evaluated at a particular yj. And it's going to be calculated by just summing up the joint PMF for random variables x and y across all xi values. And again, we can sort of see that here if we were interested in, say, the probability that our productivity is going to be 70%, and we didn't really care about knowing how that was distributed across durations, we could determine that marginal PMF for random variable y equal to 70% by just summing up the probabilities for all of these xi's. And that would give us the marginal PMF for y evaluated at yj equal to 70%. So that defines or explains that particular definition. Another thing we might be interested in is the PMF of x conditioned on a particular value of the random variable y. So we write that as the probability that we're going to get a random variable x equal to xi conditioned on the probability that y is the random variable y is equal to yj. And we know from our set theory earlier in the class that that conditional probability can be expressed as the probability, the joint probability that x and y equal xi and yj, divided by the probability, the marginal probability that the random variable y equals yj. If we come back to our plot, another way to think of this is that if we were interested in understanding the distribution of probabilities in duration, say, but we were only interested in the how long it took to manufacture something given a productivity of 70%. We would essentially sum up the probabilities along this x-axis to get our marginal probability at y, and then divide that into the probabilities at each of these xy locations here. And so basically, in that case, we would have the conditional probability, that is the probability of these events, conditioned on the idea that yj equals 70%. And that's what this quantity here is going to give us. Likewise, we could be interested in the PMF of y conditioned on x. And again, it's just going to be the joint probability that x and y equals xi and yj, divided by the probability, the marginal probability of x evaluated at xi. These conditional probabilities simplify in the event that the random variables x and y are statistically independent, and we can see that as follows. So we start with that definition of the conditional probability for the random variable x given y equal to xi and yj respectively. And of course, that's equal to this joint probability divided by the marginal probability. The key thing is that if the random variables x and y are statistically independent, then the joint probability that random variable x and y equals xi and yj is exactly equal to the probability that the random variable x equals xi, this is the marginal probability for x, times the marginal probability for y evaluated at yj. And if this is true, which is of course based on statistical independence, then we can cross out the marginal probabilities for y, and we're left with the marginal probability for the random variable x evaluated at xi. So this is a case where the conditional probability of x conditioned on y just equals the marginal probability of x equal to xi. And you can also think about it just kind of intuitively by saying that if x and y are statistically independent, then the probability that xi occurs, it's not going to depend on the probability of y, and so it makes sense that it would just be the marginal probability of x equal to xi. And exactly the same story, but just kind of flipping the variables around. If we're interested in the PMF of y conditioned on x, if they're statistically independent, that's just going to be equal to the marginal probability of y evaluated at yj. So I would like to introduce another concept, and that is the concept of covariance. And to kind of warm you up for covariance on this on dark and stormy night, I want to refer back to our definition of variance that we introduced when we first started talking about random variables. And so remember that in the case where we have a single random variable, we can define the variance as a measure of dispersion, and it's just the expected value of this quantity here, which is the random variable with the mean removed and then squared. And so this is going to give us a sense of how spread that distribution is about its mean. And it's called the second central moment. Central because we're subtracting out the mean, so it's going to be sort of centrally located around the mean, and then it's a moment because we're taking we're essentially weighting that quantity, the specific value of the random variable x minus the mean squared. We're weighting that by the probability associated with every value of the random variable, and then integrating that from minus infinity to infinity. So that was back in the day. And of course, we could also define the variance of x for a discrete distribution. This is obviously for a continuous distribution because we've got that probability density function here. We could also define it for a probability mass function, in which case the integral is replaced with the sum over all xi. Same weighting here, except we're looking at discrete values of xi minus the mean squared, and all weighted by the corresponding probability of x evaluated at xi. So that's just kind of a blast from the past, but it is a bit of a warm-up because we can define something similar to the variance for joint probability distributions called the covariance. And the covariance is going to be a little bit different. Instead of just having one random variable minus the mean squared, we're going to take the product of the random variable minus the mean times the other random variable minus its mean, and then multiply them together. And if you just look at what that would look like mathematically, the expected value of this quantity here, in the case of a continuous distribution, it's just going to be the independent variable for the random variable x, which I'm denoting here as dummy variable u, minus mu times the dummy variable for the random variable y, which is nu, minus its mean, weighted by the joint probability distribution for x and y evaluated at u and nu, integrated over u and nu going from minus infinity to infinity. So again, this would be defined as the joint second moment. It's joint because we have this joint probability density function here. Second central moment, it's second central moment because we're multiplying these two quantities together, and they're central because we're subtracting out the corresponding means. And then if we were going to look at the corresponding definition of covariance for a discrete random variable, basically exactly the same definition for the expected value, that's equal to the covariance. And instead of integrating, we're just going to sum over all xi and yj, again, including the same product of the xi minus its mean of the random variable x, yj minus the mean of the random variable y, and then weighted by the corresponding joint probability, that should be xy, sorry, equal to xi and yj. Okay, well, let's try to simplify this definition of covariance a little bit and see what happens when the random variables x and y are statistically independent. So we're trying to sort of explore, now we've got this measure of covariance, let's try to explore what happens when x and y are statistically independent. Well, by the definition of the covariance, it's the expected value of this product, and we can just go ahead and multiply this through, and so we're going to have the expected value of the random variables x, y multiplied together, minus mu x times random variable y, minus mu y times random variable x, plus mu x times mu y. And so we can distribute our expected value through these terms. Remember, the expected value is just an integral anyway, so it passes through. So we're going to end up with the expected value of xy. Mu x is just a constant, so it pulls out of the integral, so you get mu x times the expected value of y. Of course, the expected value of y is just the uy. It's the mean of y by definition. Minus mu y times the expected value of x, which of course is mu sub x by definition, plus mu x times mu y times the expected value of 1, so pulling that out. And of course, the expected value of 1 is just the moment of the PDF or PMF, which by definition is going to be unity. And so when you work all this out, basically what you end up with, because these guys end up, we end up with minus 2 mu x mu y plus mu x mu y. So we end up with finally the expected value of xy minus mu x times mu y. Okay, so this is actually how we might want to calculate the covariance between the random variables x and y. We take the expected value of the product xy and subtract the product of their respective means. So that's, I'm just translating that last result to the top of the page here. Now we're going to explore what happens if x and y are statistically independent. So let's focus in on this quantity here, the expected value of xy. By definition, that's just the second moment of, in this case, dummy variables u nu times, or weighted by the joint probability distribution for x and y, integrated from minus infinity to infinity for both variables. However, we know if the random variables for x and y are statistically independent, then this joint PDF here can be expressed as the product of PDFs or marginal PDFs for x and for y, and substituting this result here for statistically independent case, then what we end up with is we can replace this joint probability distribution with the product of the marginal distributions for x and y. And the key thing here is that now we can isolate u and fx of u and bring it out of the integral, and then integrate separately nu and fy of nu. And so basically that's what I'm showing here, that again, in the case where x and y are statistically independent, this double integral becomes just the product of two integrals. And if you look at these integrals, you realize that by definition, they're just the expected value of x times expected value of y, which is equal to mu x times mu y. All right, so if we come back to our definition of covariance, then if x and y are statistically independent, then this quantity here is just mu x times mu y, and that minus mu x times mu y is going to be 0. So that implies that when we have statistically independent random variables, that the covariance is equal to 0. There we go. The covariance itself is actually a very useful assessment of how the random variables, how strongly linearly correlated the random variables x and y are. And we can actually define something called the correlation coefficient, which is essentially a normalized form of the covariance, because the covariance itself would have units of x times whatever the units of x were times the units of y. So we just normalize that by the standard deviation of x and the standard deviation of y, which both have units of x and y, so that the whole thing is unitless. And what we end up with is a quantity called the correlation coefficient, which varies between -1 and 1. And again, if you look at the definition of the covariance of x and y here, you can see how that would happen. If it turns out that the random variable x tends to be smaller than the mean when the random variable for y tends to be smaller than the mean, and that those two are kind of strongly correlated, using that word literally in this case, then what's going to happen is that we're going to end up with the situation where these two quantities are always going to be, the product of these two quantities are always going to be positive when weighted by the probability density function. Is going to give us a positive correlation coefficient, which actually approaches unity in the limit where they're extremely correlated. Conversely, if the random variable for x is larger than the mean when the random variable for y is smaller than the mean, this product will always be negative, and so we'll end up with, when you carry out the integral, a correlation coefficient which is closer to -1. And let me just go through some pictures from the textbook kind of illustrating this. So here's a case where we have realizations from the random variable y plotted against realizations for the random variable x. And in this case, these realizations are very strongly correlated with a correlation coefficient with +1. So you can see they're very, very linearly correlated. Here's another case where the realizations for y and x are negatively correlated. So as we increase, as the realizations for x increase, the realizations for y tend to decrease. So that would be a case where perfect negative correlation where rho is equal to -1. And again, a perfect positive correlation of 1 ends up with all the data plotting along a straight line. A case where the correlation coefficient is 0 is shown here, where basically you just, all the realizations for y and x appear to be statistically independent. When we get a realization for y, it really doesn't depend on the realization for x, and so the plots end up, or the points end up plotting kind of randomly, like a scattergun across this space, possibility space. And then if our correlation coefficient is somewhere between 0 and 1, we tend to get a result like this. Actually, you know, as an experimentalist, I would say this is a really excellent correlation. If I ran some experiments in the lab or the field and they came out this nicely correlated, I'd be very, very happy. And you know, basically that is showing a very strong correlation between realizations of y and realizations of x. And then according to our analysis, that would suggest that that these two random variables, y and x, are not statistically independent. Now, the correlation coefficient only captures sort of linear relationships between the random variable x and y. And so here's some situations where we have, you know, very clear kind of analytical forms for the realization of y against x. You know, so here we've got kind of a sine wave. Here we have sort of an ellipse on its edge. And in both of these cases, if we were to calculate the correlation coefficient, it would be 0. So just because the correlation coefficient is 0 doesn't mean there isn't some sort of analytical relationship or some strong relationship between x and y. It just means that there's not a linear relationship between x and y. Okay, so given all of that as background, now I wanted to kind of go over that example that we started in class of essentially looking at the joint probability mass function of midterm scores from our first midterm. And so the question statement looks like this. Based on the first midterm scores, your professor extracted a list of student scores together with the standing of each student, that is, whether they were a sophomore, junior, or senior. And given that information, you're asked to do the following. Prepare a joint PMF of the data in which one random variable is score range and the other random variable is standing. For score range, divide the scores into the following ranges: 20 to 40, 40 to 60, 60 to 80, and 80 to 125. So that's the first task. We need to create that joint PMF. The second task is to prepare a joint CDF corresponding to the PMF prepared in Part A. And then we're to make sure that the joint CDF obeys the required limits for joint CDFs. Part C, we're asked to prepare marginal distributions for the two random variables. What is the interpretation of these marginal distributions? Part D, we're asked to prepare PMFs for scores conditioned on standing, being sophomore, junior, or senior. Then we're asked to prepare PMFs for standing conditioned on the test score. And then they're asked, what can we conclude from these results? And then finally, we're asked, are the scores and standing random variables independent or dependent? In other words, are the scores and class standing correlated or uncorrelated. Okay, so that's our task. It's kind of a big job, but luckily you don't have to do it. I do, so it works out okay. Now I'm going to come over here to see. I think I need to select my Excel spreadsheet. So I'm going to come back over here and then select the spreadsheet. And so hopefully you're seeing the spreadsheet. You are, I think. Okay, so now we're looking at the Excel spreadsheet, and we started out with basically what we were given were kind of the raw data. So we've got 2 columns of data. I've got midterm score and then class standing. And again, SO stands for sophomore, JR stands for junior, and SR stands for senior. And if you look at the midterm scores, you see they range from kind of lows of in the 20s and 30s up to values as high as 113. I think there's even 120 here somewhere. So, well, certainly 117.5. So anyway, quite a range of scores. I also, just for some of the other calculations we're going to be doing later, I arbitrarily defined a sort of discrete number associated with the class standing. So I let sophomores be the number 2, juniors be the number 3, and seniors be the number 4. Notice we have no freshmen, so there are no number 1s in this class standing. That kind of brings up a point, which is that with these probability mass functions, oftentimes you're called upon when you're trying to create a random variable to assign a number to something that's a little bit more conceptual, like in this case, junior standing. That's not really a number, but in order for us to do some of our calculations, we have to give it a number. And so in this case, I just gave it an index, 2, 3, or 4, depending on whether you're sophomore, junior, or senior. Okay, so remember what we did was we basically took all of these standing and score pairs, and we imported them into another Excel spreadsheet, and we sorted by midterm scores. So we had scores running from lowest to highest, and then we counted the number of sophomores that got basically in the range 20 to 40, midterm score 20 to 40, and then we calculated or determined the number of sophomores that were had a score in the 40 to 60 range, 60 to 80 range, and 80 to 125 range. So we ended up with this nice frequency diagram or table here. So again, we've got columns are sophomores, juniors, and seniors, and then the scores that each of those different categories received on the test. And then if you did, if you summed over all of these individuals, you end up with 99, which is correct. We've got 99 students enrolled in the class. So that's a frequency distribution or frequency table. It's a good start, but we want a probability mass function for this problem. And so that means we're going to have to convert those frequencies, that is how many people were in each of these cells, into a probability or percent. And the way that we do that is we divide each of these cells by the total number of students, which is 99. And so I've done that here to create the probability mass function, which is indicated by the kind of highlighted blue box right here. So, so these numbers now are essentially probabilities. Now, if I wanted to, one of the questions was related to marginal distribution. So I was supposed to create a marginal distribution for standing, class standing, and then also a marginal distribution for scores. And in order to create the marginal distribution for class standing, all I have to do is basically sum up all of the probabilities associated with sophomores, because I don't really care what score they got. I just want to know what the marginal probability is for standing. And so when I sum these guys up, I get about 27% of the students who took the exam were sophomores. And you can just make sure that's what I did. Oh, well, it's just a number. But anyway, trust me, that's the sum. We can actually calculate it here. So I'll just sum from top to the bottom, and I get exactly the same number, yes, 0.272. So about 27.3% of the students who took the exam were sophomores. Do the same thing for the juniors. So I sum up over all of the probabilities scores here for juniors, and I get about 54% were juniors. When I do that for seniors, I get about 19% were seniors. So in this case, the marginal distribution for standing is just telling us what percentage of students were sophomore, juniors, and seniors who took the exam. Likewise, I could compute a marginal distribution for score. And in this case, I'm basically saying I don't care whether the students were sophomores, juniors, or seniors. I just want to know what the probability was that they got a particular score. And so the fire alarm's going off here. I'm just going to finish this discussion of the single marginal distribution, and then I'm going to have to run out of the building before it burns down. So basically, when we do that, we sum up the probabilities associated with this particular score, and we get 9% of the test takers had a score of 20 to 40, 24% had a score of 40 to 60, 36% had 60 to 80, and then 30% had 80 to 125. And so with that, I'm going to stop the video, and I'll pick it up when the fire alarm isn't going off. Okay, I'll talk to you later.